Exercise 21.5, question 7. So in this question, we have a golf ball projected at a speed of 30 root 2 at an angle of alpha. And if we define our origin as the T where the ball is hit from, and upwards as Y and horizontal as X, part 1 asks us to find the equation for Y in terms of X and alpha. So at a given time T, what do we know? Well, the displacement at a given time T is X and Y. The acceleration is constant, it is 0 and negative g, but in this case we are told that we can use g equals 10, so 0 and minus 10, and we know that the initial velocity is 30 root 2 cos alpha 30 root 2 sine alpha. So substituting this into the equation, r equals ut plus a half a t squared, we get xy equals 30 root 2 cos alpha 30 root 2 sine alpha times t plus a half of 0 negative 10 t squared. And writing down equations from each component, in the horizontal component we get x equals 30 root 2 t cos alpha, and y equals 30 root 2 t sine alpha minus 5t squared. And then if we rearrange this one here for t and substitute it in, we're going to get an equation in y, x and alpha. So t equals x over 30 root 2 cos alpha. So putting that in here, we get y equals 30 root 2 times x times sine alpha over 30 root 2 cos alpha minus 5 lots of x over 30 root 2 cos alpha all squared. We do a bit of simplifying on this. We can see that the 30 root 2's cancel. Sine alpha over cos alpha is tan alpha. So this is x tan alpha. And if we expand this out, we get 5 lots of x squared over 30 root 2 squared. Well, that is 30 squared times 2, which is 900 times 2, which is 1800 cos squared alpha, which is x tan alpha minus, well, cancelling a factor of 5, there are 360 5s in 1800, so this is x squared over 360 times 1 over cos squared alpha, which is sec squared alpha, and then we're using the identity that sec squared alpha is identical to 1 plus tan squared alpha. We get the result we are asked to show, which is y equals x tan alpha minus x squared over 360, 1 plus tan squared alpha. Okay, in part 2, we are told that the golf ball just clears a tree 5 meters high, which is 150 meters horizontally from the tree. Find the two possible values of alpha. Well, what we know here is we know that 150 meters away there is a 5 meter high tree, and we want to think about what possible values of alpha would mean that it just clears the tree. Well, there are two possible situations we can imagine in this case. We can imagine the situation where it just reaches the tree on its way up, or where their alpha is quite small, or we can imagine the other situation in which it just reaches the tree on its way down, and then you've got quite a large alpha. So we can see there are two possible values of alpha where it just about touches the top value of this tree. Okay, but what do we know is true in this case? Well, we know that at this point here, we know that x is 150, and we know that y is 5. So we take these two values here and put these into here, we get a quadratic equation in tan alpha, and therefore we can solve it for tan alpha. So you shouldn't be surprised that we get two possible values of tan alpha. So let's go ahead and do that. We get 5 equals 150 tan alpha minus x squared, so 150 squared over 360, 1 plus tan squared alpha. Well, doing a little bit of simplifying on that by multiplying through by -2 and then dividing by 5, you end up with the quadratic equation 25 tan squared alpha minus 60 tan alpha plus 27 equals 0. And I'll let you verify that for yourself. And again, with a little bit of work, we can see that that does factorize, and I'll let you do that verification for yourself. But if you factorize this, we end up with 5 tan alpha minus 3, 5 tan alpha minus 9 equals 0, which gives us that either tan alpha equals 3/5 or tan alpha equals 9/5. And we can see that as tan alpha is an increasing function when alpha is between 0 and 90, the 3/5 one corresponds to the small value of alpha, and the 9/5 corresponds to the large value of alpha. Okay, part 3, we are asked to use the discriminant of the quadratic equation in tan alpha to find the greatest distance by which the golf ball can clear the tree and find the value of tan alpha in this case. So, firstly, I'm going to take our quadratic equation from part 1. I'm just going to expand it out and write it in the way of we're kind of more used to as a quadratic. So that quadratic equation is y equals minus x squared over 360 tan squared alpha plus x tan alpha minus x squared over 360. And what we're interested in is we want to know what is the largest value of y when it passes over the tree. So if we take this projectile here, we want to know when it passes over the tree, how large can y be at the point where it passes over this tree? And we know that this distance here is 150. So we want the largest possible y when x equals 150. So we make that substitution, we end up with y equals minus 150 squared over 360 tan squared alpha plus 150 tan alpha minus 150 squared over 360. And this we can see is a quadratic in terms of tan alpha. And we want to think about the largest possible value of y here. Well, we could think about this as a function here, as this axis being the y-axis, and this being the tan alpha axis. And this is some kind of quadratic with a leading coefficient that is negative, so it's something a bit like this. And we can see here that what we want is the largest value of y, which is here, and the value of tan alpha at which this occurs. So what we want to find is this point of the quadratic. Well, we could differentiate this here and find stationary point. We could complete the square, but it asks us to use the discriminant. And at this point here, if I were to put in a value of y, we want the point here where there is only one solution. We don't want a value of y up here because there would be no roots to the equation. We don't want a value down here because there would be two roots to the equation. So we want to know when the quadratic equation 0 equals minus 150 over 360 tan alpha plus 150 tan alpha minus 150 squared over 360 minus y. We want to know, when does this quadratic equation have exactly one root? Because that is going to give us this point here. So we want to know when is the discriminant of this whole equation, including this y here, is equal to 0. So we want b squared minus 4ac equals 0. Well, b squared is 150 squared minus 4 lots of minus 150 squared over 360 times by c, where our c here is minus 150 squared over 360 minus y. So we can solve that for y. Well, we get 150 squared. If we take out a factor of minus 1 from each of these two brackets, we can see that this is, and 3 negatives being multiplied, so this is minus 4 lots of 150 squared over 360, 150 squared over 360 plus y. Well, adding to both sides, we have 150 squared equals 4 lots of 150 squared over 360 multiplied by 150 squared over 360 plus y. Well, we can cancel a factor of 150 squared, multiply by 360 and divide by 4. Well, that is 90. So 90 equals 150 squared over 360 plus y. So y is 90 subtract 150 squared over 360, which is 27.5. And that's not quite the answer to the question, because we want to know how much does it clear the tree by, and actually we don't want this whole distance here, we just want this distance here. So what we are looking for is 27.5 subtract 5 is 22.5 meters. So it clears the tree by 22.5 meters. We are also asked to find the value of tan alpha in this case. Well, if we go back to our quadratic equation here, we are essentially looking for this value of tan alpha here. So what value occurs here? So we're essentially saying, for what value of tan alpha does the maximum point occur? Well, we know that tan alpha is equal to minus b plus or minus b squared minus 4ac all over 2a by the quadratic equation. But we know that b squared minus 4ac in this particular situation is equal to 0. So in this particular situation, tan alpha is just equal to minus b over 2a, well, minus b is minus 150 over 2a, which is over 2 lots of minus 150 squared over 360. So it is minus 150 over minus 2 times 150 squared over 360, which is 360 over 300, which is 1.2. So the value of tan alpha is 1.2. Part 4. In the final part of the question, we are told that the hole is 160 metres from the tee. So we have a tree of 5 metres. There's 150 metres from the tee. And then we have a hole here, which is an extra 10 metres. And we are asked to find the greatest height the tree could be without making it impossible to hit a hole in one. So we definitely want to be able to have a projectile that will go and land directly in the hole. So there are clearly situations in which this tree is going to be too big. A tree like this would mean this wouldn't be possible. So what we want to find is when x is 160, because we need it definitely to be able to go into the hole. So when x is 160, well, what is y? Well, that is when it is in the hole, so y is 0. So we can set up our quadratic equation with these two bits of information here. So I'm going to take the same quadratic equation as before, which is this one here, and just substitute in those two values of x and y. So y is 0, we get 0 equals minus 160 squared over 360 multiplied by tan squared alpha plus 160 tan alpha minus 160 squared over 360. And that is a quadratic equation in alpha, and it's not a particularly nice one. So just solving that using your calculator, you end up with tan alpha equals 9 plus or minus root 17 over 8. Oh, it's a little bit strange that we get two values of alpha here, but if we stop and think, it shouldn't be, because again we have the situation where the ball goes really high and down into the hole, but we also have a situation where the ball goes really low and down into the hole. And we're asked for what is the maximum value of the tree where it's possible. So it doesn't really matter about the low one, because it's still possible for you to take the high shot and get it into the hole. So actually what we're interested in is the situation, if not even the high shot is going to get you in the hole, then, because the tree would be in the way, then it's no good. So this is the situation we were looking for. We're looking for the largest value of alpha. So what we're interested in here is when tan alpha is equal to the largest value. So 9 plus root 17 over 8. Well, what do we now know? Well, we know that the height of the tree is just going to be the value of y when x is equal to 150. And we have our quadratic equation. Our quadratic equation is the same one as before. It is this one here, but it might be more convenient to use the form given in the question. So we have y equals x tan alpha minus x squared over 360, 1 plus tan squared alpha. And we know at this particular point, x equals 150, and we want to find the value of y. But we know that tan alpha is equal to 1 plus root 17 over 8. So we know that y equals 150 lots of 9 plus root 17 over 8 minus 150 squared over 360, 1 plus 9 plus root 17 over 8 all squared. And just typing that into our calculator, you get y is approximately 15.38 meters.